I want to take you on a trip on both the solar system and the nanometer range. It's quite the opposite. The talk will be more or less two parts. The first, I want to give you a little bit of context about the space agency and space applications before we actually go into ultra-deep submicron and what we're planning to do with this kind of technologies. By the way, ESA is celebrating 50th anniversary this year. We're very happy. And what is ESA? We have this flags. If you visit us in one of the facilities, you will see the flagpoles with all these flags. It is some 28, I think, today. They're decorative, but they also stand for our member countries. The member countries is what founded ESA, and it is what defines ESA, and it's what makes ESA very diverse, sometimes a little bit complicated. And you need to know this in order to understand and work with ESA. We have all of the EC countries are either full member or preparing to become a member. And we have 3 countries which are not in the EC, but in ESA, that's the UK, Switzerland, and Norway. ESA is organized in several pillars, or some call it a matrix. So you have application domains in the vertical, and you have supporting domains in the horizontal. The supporting ones are the ones here with the yellow lines. I think we're some 5 people from ESA here, from software, from data systems, and from microelectronics. We're all in the technology department. We're supporting the applications. We are the ones interested in the very details of technology. So ESA is a funding agency with technical competence, let's say. From all these different applications, I want to pick out a few, a little bit arbitrary, but I took the ones where I can make a point about the diversity we have in applications. I always get questions like, which technology do we need? Is it FPGA or ASIC? And my answer is always, we need all of them. Because what we do is so diverse, so we need some technology here and the other one there. And it depends case by case. So this is a slide from our colleagues in science with an overview of spacecraft exploring other celestial bodies. So we have spacecrafts going to, not all, but most of the different planets. If you go closer to the sun, there's no shortage of solar power. It's getting a bit hot. Components need cooling. If you go away from Earth, go away from sun, it gets dim and cool. And either you have batteries or you have radiothermal generators. You don't get far with solar panels if you want to fly to Neptune. There's not much sunlight there anymore. There's also science around Earth. They're mostly telescopes. They're looking anywhere but Earth. They're looking away from Earth. And I'm sure you remember things like James Webb Space Telescope or Gaia, which is just shut it down, I think, 1 week ago after a tremendous operating life. Those telescopes are in Earth orbit, or they're in orbit around the Lagrange point, in the same orbit that Earth has around the Sun. They all have in common, those have in common that the radiation requirements are modest. If I go one slide back here, it depends where you fly. Normally in interstellar, in interplanetary space, there's not too much radiation. There's a lot of radiation around planets that have a magnetic field because they protect the planet's surface and they collect radiation particles in the magnetic field. Earth does that. We wouldn't exist without that. And the greatest, by all means, greatest example is Jupiter. It has a massive magnetic field. And if you want to fly a mission to Jupiter, you need components that are beyond immune. They have to be massively immune. There's a huge range of requirements that we need. That's for science. Completely different, Galileo. Galileo apparently is in Earth orbit. It's not a satellite, it's a constellation of satellites. They're in low Earth orbit. Radiation requirements are modest, but it has strategic and security requirements, very stringent. It's the flagship infrastructure project of the EC. It's not owned by ESA. The technical components of the space segment are delegated to ESA, but Galileo is financed and owned by the EC. Beyond the Galileo that we have today, there is a Galileo 2 in preparation, and Genesis, and LEO PNT. So we're busy with new missions where things that I just said about Galileo hold true, but it's a new technical generation. ARTES is a funding line that stands for telecom, or now communication and security. That's another application that takes place in Earth orbit, mostly in low Earth orbit with moderate radiation requirements, but not only. There's also the middle Earth orbit, and there is a geostationary orbit where you need more robust components. Telecom is the application domain that has the most stringent performance requirements. They have massive bandwidth. They have requirements very business-like time to market matters a lot because there is a lot of competition. You have to be in the market and make money, otherwise telecom is not affordable. But if you have customers, then there's a lot of money, and that's why telecom is the driver for our microelectronics efforts, like an early adopter of new technology. That's the second part of the presentation. RISC-V is coming up in that sense. It's part of telecom. RISC-V will be something roughly comparable to Starlink, but owned by the EC. And again, the EC is delegating the technical work to ESA. And ESA is going to delegate the technical work to industry. So you need to understand ESA. Moonlight is a project in a program, a long-term program in a collaboration with NASA, all about the moon endeavors that we're planning. It's a whole system. We have different application domains with their different directorates and their own organization, and you see some funding programs here. I'm not going to read the numbers, maybe just the total, 17 billion. And this is what we call the mandatory budget. Each member country, each of the 28 member countries is contributing a fraction of their national GDP because they commit to that. And that's the budget that ESA is planning how it's going to be spent, always with the approval of the member countries and the delegations. Complement to that, there is a budget of a little bit less than 8 billion. That's the so-called optional budget. And this is where the ministries of the countries and the delegations decide case by case what they're interested in. It's important to understand that ESA, as I already said, is owned by its member countries. The member countries are the stakeholders, and they decide what they are interested in. And the member countries have common goals, but they also have national goals. So you will find specific areas where only one or two countries are interested in. And if you apply for any program, for any activity with ESA, you will find details of the procurement process that you will understand better if you think back to this information. This is just for reference if you go back to the slides, annual budget of last year. And here's the transition to the more technical part. I mentioned already we have a magnetic field, and that magnetic field is shielding us, but it's also funneling radiation in some part of Earth environment where we eventually fly through. And then we need more red hard parts. We're living now, you know, the political climate. I will not go deep into it, but there was a long phase of globalization without limits. And then we had, unfortunately, COVID. And some people woke up and said, hey, where's my supply chain? And now we're 5 years after that, but there's other factors having impact on our supply chain. So globalization seems not to be the only answer. And politics is waking up, and you have for sure heard about the CHIPS Act. CHIPS Act is basically is doing many things, but it's providing funding for foundries, for a lot of things that are needed for the supply chain, and eventually for producing chips. So we all agree that Europe needs its own supply chain that we can depend on, and we're not depending on countries that are not suddenly not favoring us. What does it mean? I am not explaining the CHIPS Act. I'm more interested in the EEE space components, which is a fraction of what came from the CHIPS Act. In the ministerial conference in 2022, it was decided to give a certain funding in this direction, with the objective to produce technologies and technology capabilities for the purpose of high performance ASICs and FPGAs in space for our space applications. And in the meantime, since 2022, we have succeeded to define a couple of activities and implement them, and started some of them. And we're doing this not alone, we're doing it together with national agencies. The member countries not only have national interests, they also have, many of them have national space agencies. We work with them together. Of course, there's the EC. It's a great factor in Europe, thankfully. And the industry that most of you represent. Approach has to be collaborative. We cannot do anything alone. The field is way too big, and it's not enough to throw some money into the wind. We have to align on what is needed and how to achieve it, and focus the different funding possibilities. So what we do is we make a lot of meetings, we make roadmaps, we coordinate with the EC, with the European Defence Agency. We have a joint task force for road mapping and bringing ideas together and identify gaps. A number of different technologies have been defined in different regions. There is photonics, there is gallium nitride, there is quantum computing. Myself, I'm interested in microelectronics, so I'm sharing with you what we're doing in ultra deep submicron. That's the topic here today. Anybody can go to Foundry and tape out a chip, provided you send some money with your tape out, right? It's not exactly the case. If you go for very advanced technologies, the Foundry will ask you about your business case. They will ask you, how many do you need? I say 1, they say 1 million. I said, no, 1. It's a bit difficult. Again, the application domains where we need big volume is telecom, because they are building constellations. There can be 10,000 satellites, and each of them having 1,000 channels, so you need 1 million chips. That's good. But we also want to fly to Saturn and make pictures, and we really need 1. And if we need the performance, then we need this technology to enable the mission. Well, that's a problem. And that's just a die. How about packages? How about assembly? And the whole supply chain is more than the die. Usually as a ASIC designer, we forget that it does not stop at the design. So we're tackling the whole supply chain, not just fabrication. And again, with the EC and with different teams that communicate in all directions, hopefully successfully. That's what I just mentioned. That's the technology lines in our EEE program. So it includes the test facilities, it includes passive components, gallium nitride and silicon carbide, photonics, UDSM is here, packaging, and qualification. We have, before the EEE initiative, we already have endeavored with Nano Explorer. Where's Alp? Are you still here? Or traveling home? Maybe he's gone. We had the talk of Nano Explorer. They have started the initiative to build a European FPGA from scratch. It's not easy because you have a hardware part, you have a software part, you need a whole ecosystem, and you have to convince the designers to use it in the end. So it has to be excellent, and it has to be successful, and it has to be competitive. And we have started that somewhere around 2016 with NanoExplore. And today we have already several generations of this. It's called a Brave. You have heard about it, I'm sure. On the table with test results. I think there cannot be a microelectronics talk without some of this. I'm very sad that Mr. Moore passed away and we're a little bit in the post-Moore era. The marketing departments don't know that yet, but the technology scaling does not take place as it used to be. There's a lot in this graph. We could discuss it for 1 hour, I think. And one thing you can see is that down to 16 nanometers, we had a lot of technology in Europe, and suddenly it's all gone. The European component vendors that had their own foundries decided it's cheaper to produce in Taiwan, so they become a design house, basically. And the state-of-the-art technology until recently was only available in Taiwan. What happens very recently is that the US and Europe and maybe some other areas support TSMC to build foundries in our own continent, but still under the control of TSMC, no surprise. Another observation is when I look back in my career, that's slightly more than 20 years, from the announcement of technology that it became available for industry until the moment when we use it in space, it's about 7 years. We're 7 years behind. Not because we're lazy, but it takes the time. We have to put on, we have to get the funding, we have to get access to the supply chain, we have to make our RUD testing, and we have to make it ready. It takes time, always takes time. So where are we now? 7 nanometer just became available. TSMC saying if your name is Apple or NVIDIA, you can have 2 nanometer. If you have volume otherwise, you get 3 nanometer. And if you're academia, you can have 7 nanometer. That's where we are. So let's go 7 nanometer then. There is something that is still following the exponential law, and that is the mask cost. I tape out in 7 nanometers, became cheaper last year. It went down from 10 million to 8 million. For a university project, that's very steep. It's still steep for a whole space agency. We have to combine different activities and make joint tape outs, and then we still struggle to get 8 million together. And then Taiwan is not Europe, isn't it? Ideally, we would support technologies that are actually produced in Europe, where all the IP and knowledge is in Europe and it's free of export restrictions that are not in our control. So what do we have? We have ST, microelectronics in France, with 28 nanometer FD-SOI. We have Global Foundry, 20 nanometer FD-SOI, US company with a German foundry. We have Intel with 7 nanometer in Dublin. Again, it's a US company. And this one, Global Foundry is making efforts to offer the technology free of export restrictions. Intel is not. This one is subject to export restrictions. Then for the future, ST is working on shrinking 28 down to 18. CA Leti have a project going on for 7 nanometers. Intel is shrinking down to 4. Still, it will be under export restrictions. Interestingly, the ESMC project, that's TSMC with European Automotive. That's, you might have heard that Germany is subsidizing TSMC in Dresden, Germany. That will go down to 12 nanometer as we expect. And if you look in this list today, there is no 7 nanometer. So everything that I will say in the next slides about 7 nanometer is with the TSMC foundry in Taiwan as a backend. Decision is taken. We are going to use 7 nanometers and make the technology useful for space applications. What do? We need to focus on those applications, on those chips where we expect at least some volume, where the costs are somewhat handleable. And these are normally general purpose processors that can be used across very different applications. And FPGAs. FPGA here is not about using FPGA, but creating FPGA. And then we have DRF and digital beamforming. This is for RISC-V. This, as I said, is a constellation, so there are big volumes to be expected there. DSPs are candidates and domain-specific accelerators. Still, I'm talking too much about foundries and dies. It doesn't stop there. We need CAD tools. We need the access. We have to be able to afford them. We're not even talking about replacing CAD tools. If we want to be sovereign, we should have our own European CAD tools. We're far away from that. Assembly, packaging. Packaged material today comes mostly from Japan. It's assembled somewhere. We have very little capabilities in Europe on a system in package. And system in package is important because it can help us to transition between more affordable technologies and 7 nanometer or smaller. So you can have chiplets with the processor and maybe with an FPGA, and then mix them with your specific application-specific chips and assemble together in a package. You have a system. Wonderful. But it takes technology, and it's not as easy as saying it. We have planned many and started some activities in this EEE initiative. We started with so-called UDSM-0. That's an early evaluation of 7 nanometer. A contract has been awarded to IMEC. And they are testing. They have designed and submitted to TSMC 2 test vehicles, one for analog and the other one for digital building blocks on chip. And we're going to characterize them electrically and under radiation. This activity started beginning of last year, and it will conclude somewhere in the autumn this year. And then we know the capability of 7 nanometer with respect to space applications. And we're going to use this for the next activity, that is UDSM1. This activity has been awarded end of last year and kicked off in December last year. It has been awarded to Geisler as a prime contractor, and together with IMEC and IMST, who are doing different building blocks. I have more details on that on the next slide. And then the publication of the invitation to tender for UDSM2 is imminent. Has to happen in the next quarter. It's April already, right? This quarter. Should have said UDSM1 is focused on the building blocks for the design of general purpose processors. UDSM2 is focused on creating building blocks for FPGAs. So some building blocks are the same, some are not. FPGA tiles you don't need in processors, do you? And then we have some accompanying activities. There will be one with a ZS for HSSL, and we're planning some building blocks for RF. All of this eventually will be put into an IP portfolio of building blocks for anything, any ASIC that is to be designed in 7 nanometers. And 22 nanometers, sorry, I haven't mentioned that yet. The scope of this whole program also includes 22 nanometer, with the focus on 7. Once this first wave of activities is close to being finished, we go into the second wave, where we produce actual products in UDSM3, the general purpose processor, and in UDSM4, product FPGA. We're not talking about the old school pure processor and pure FPGA, but rather system on chip, where the processor, why not, can contain a small eFPGA. And in UDSM4, the FPGA SoC should also include a small processor core. And USMRF, again, this is targeting at RISC-V to satisfy their very specific needs. RISC-V is just, how to say, it's still very much in the definition phase. So it's too early to know the requirements, we're only assuming. Now we're back to, I'm going to talk about USM 1 and 2 with a little bit more detail. The 1, it was planned to include a die-to-die interface in 28. This is not in the baseline anymore. What is in the baseline is the I/O and core library for 22 nanometer global foundry technology and DDR4 interface and a data router. And in 7 nanometer, we're doing a RISC-V chiplet. That's why I'm here. And a fully fledged design library. The 102, we call it UDSM2. That is the building blocks for the FPGA. It has to be put in a proper procurement process, so we will publish an invitation to tender. Nevertheless, we have already talked a lot with industry, and we expect NanoExplore to put a bid with their selected subcontractors. And hopefully we can award a contract to them early in the 3rd quarter this year. And it will include CRDES for interfaces, PCI Express interface, DDR4 interface, die-to-die interface, hopefully user express. And we will go deeper into SIP packaging technology. Here's a picture of Sandy. Signing the UDSM1 contract with our director. It was a good event. That happened last December. You see here the expected countries in the consortium for UDSM1, respectively UDSM2. This is back to the fact that it's not only UDSM, it's not only 7 nanometers. We need all kind of stuff. We are thinking of parallel computing, embedded computing. We need standalone memories. We need memory IPs. We need power management, digital interfacing. We need converters of all kind, system package I mentioned several times, and a lot of digital IP. So there remains enough work for everybody. I think that's the end of my presentation. I thank you, and there's a little bit of time for questions. And before you hammer me with questions, if you're interested in full custom ASIC design, please visit us in Lisbon at Amixa. Thank you.